Okay. So plots and maps in R. I'm going to talk a little bit about just simple plotting to start. So we had used this data set quakes before, and we're going to use it again here, especially in the beginning. So I'm going to load up some packages, scales for opacity. So when you're plotting things, if a lot of them overlap, you might want to use some sort of opacity of maybe 0.1 or 0.4 or something like this. So you can kind of see the density of the points that you're plotting on top of one another. You'll see some examples in a moment. Lubridate is for dates. I think I use it once or twice in this case. And then SF is for simple features. So this is for maps and things like this. So anyway, if we wanted to just plot these two variables, the magnitude and the number of stations that registered the earthquake, we'll see a pretty gross looking plot. So it just has circles that are black and empty. It has pretty terrible names here. It just has the vector names. It has just not much to it, right? So there's all sorts of different things you can use to customize your plots, and I'll use some of them below, but just to kind of go over the list here. We have labels, so X lab, Y lab are just X and Y labels. Main is the title here if you wanted to title something. Though I usually like to title my plots in LaTeX, so I'll do that afterwards. You can use XLim and YLim. These are allowing you to set boundaries. So for example, this just naturally goes from 4 to maybe 7. But if you wanted to extend it to 10 and you wanted to show that there was nothing past 6.5 or 7 or whatever this is, you could do that as well. So you can kind of scale your limits of your plot however you want. By default, R will just automatically fit the data that you're plotting in the plot function. Colors, there's all sorts of colors you can use. In fact, there's probably too many colors. Here's a PDF with all sorts of colors you can use in R. It's 7 pages worth of colors. Some important ones you should think of are, just obviously red, blue, green, whatever, but any sort of HTML colors. All of those color names map directly. So red in HTML, it's a bit of a softer red. It's not so intense. It's called tomato. There's Dodger blue. Those are a little bit nicer colors, but you can do all sorts of stuff. You can also feed in numbers and R will convert them into colors. I think it has 7 or 8 options and it'll just cycle through them. So if you do 1 through 8 will be all unique colors, but then once you get to 9, it'll rotate back to 1 and so on. So if you want any sort of variation just to use numbers, you can do that as well. Type, so there's a couple different ones. You can use P for points, L for lines, B for both, so it'll plot lines and endpoints, and then H for histogram. I'll show examples of all of these below. So PCH is the point type. So there's a bunch of types you can pick. So if you pick 0, it'll do this empty square. 1 is the default empty circle, and so on. So 19 and 20 are the ones I usually use where they're filled in. I just think it looks better. But you can do all sorts of shapes. You can also type in PCH equals and then A, quote A, and you could just plot A's if you want, or B's or something like this. Some other things, there's line types. So you can check out what line types. Apparently you can't. Here's an example of line types in R. So 1 is the default solid, 2 is dashed, 3 is dotted. These are the 3 I pretty much use. If I have to use more than this, I'll probably start using different colors or something like that, or thicknesses. In order to do thickness, line thickness, it's LWD. Line width, 1 is the default, 2 doubles that thickness, and so on. CEX is the point size. So again, default is 1. 0.5 is half of that. 2 is double that. BTY is border. So if you don't want this black box around your figure, you can get rid of that, and you'll just have the axis with the dashes. and then everything else will be blank. And then there's also a ton more if you just use this question mark plot. You can find all sorts of commands. So that's just for the regular plot, but there's all other ways to plot. So you plot a data set, but you want to add to it. You want to add more, different data set on top of it. You can use points to add points, lines to add lines, segments. This is going to be little line segments that you want for like confidence intervals, or maybe you want to show like, if you have a diff and diff, maybe you want to show like part of a horizontal line, then a vertical line, then another horizontal line going across. Polygons, if you want to do confidence intervals, but you want like the shape, if you kind of know what I'm talking about, I'll show examples below. AB line is just for all sorts of straight lines that go across the entirety of the plot. So vertical lines, horizontal lines, diagonal lines, all sorts of stuff. And then finally, legend. So legend will be, if you want any sort of legend, you can customize it in a million different ways. Very similar to plot, but again, so we'll just go, just go through some examples. I'll play with this one a little bit and then I'll just move forward. So if we wanted to really kind of beef up this scatter plot, here are all sorts of things I added in here. So I have my X label is magnitude, my Y label is stations, main, PCH is 20, that's the solid small dot, type equals P. The default for plot is P, so this isn't really changing anything. Color, I'm using something from that scales package. If you type in alpha, the color, and then this is the opacity. Opacity runs from 0 to 1. X limits and Y limits. So if we pop this open, we'll see it looks much different. I mean, it's the same data, but it looks much more appealing. Maybe you have different preferences for colors or other lines, but I've also included, I've used that AB line function a couple times. So this one is V equals 4 is just a vertical line at 4. So you can see here, we created this right here. This next one is a horizontal line at 0. Line type is 2, so that's dashed. And the color is gold. It's really hard to see. It's right down here. I just wanted to show different colors. AB line 0, 1. This is going to create a 45-degree line. So in other words, intercept is 0 and the slope is 1. And that's going to be red. And then finally, I can also include just a regression line, a line of best fit. So I'm just using the LM function, and it's taking the two coefficients, whatever the intercept is and whatever the slope is, and it's plugging it into AB line for me. So I don't even have to do this 0, 1 or type it in. I could just type in the regression line and it'll plot for me. And I've made this medium sea green. So you can see you can do all sorts of colors. Okay, someone put in the chat, but looks like it was handled. Okay. So that's this one. So the next thing I always like to do is make aggregate plots. So make a plot, aggregate it, and see what the relationship is per value. So for example, in this case, it's a little bit hard to see if the functional form is straight like this or if there's some sort of curve to it. So what I'm going to do here is I'll use this aggregate function, and I'm going to aggregate the number of stations by the magnitude of the earthquake. I'm going to find the average. So when I plot this, it's going to be the black circles. So you can see this is the average stations per magnitude. You can see it almost looks like a cubic function where it's kind of bending here and then bending again here. So what I did here was I generated a cubic regression. Then I aggregated the fitted values and I plotted those, and I say, okay, it fits pretty good. You can't use this function right into the AB line because this only takes linear functions, not cubic or quadratic or anything. Okay, this next one, I'm gonna use some confidence intervals. So I've already aggregated by the mean, that's ag. Then I'm gonna aggregate stations 5 magnitudes, and I'm going to use a standard deviation function. And then I'm going to find the n using length. So I'm just going to be able to kind of generate confidence intervals for each of these points. So if I'm just going to plot my regular thing I had before, this time I'm going to use this lim where my magnitude has to be less than 5.5 because these are very infrequent. So when I plot this, it's going to look exactly like this, but then I'm going to add these segments. So the segments are going to have an x0 and an x1, and because each segment has a beginning and end point, the beginnings the x values are going to be the same because they're just going to be vertical lines. So my x0 is going to be the magnitude, and the x1 is going to be the magnitude. Then the y0, this is where I'm going to make the variation in the vertical direction. I'll do the average minus 1.96 times the standard deviation divided by the square root of the sample size. So this is going to give me the confidence interval. So this is the lower bound, this is the upper bound, and it's going to create these little confidence intervals for me. Now, the thing to notice is, okay, great. Well, it got cut off here, and you can imagine if this was more infrequent, it would get cut off here as well. So you might have to adjust the limits of your plot to include these things. So in this next one, I'm keeping the segments exactly the same. Nothing's changed. But this, I'm adding the argument ylim, and I'm going to say I need the minimum of the lower bound and the maximum of the upper bound. So when I plot this, it's going to fit inside of the axes. Okay. This next one is going to be plotting polygons. So instead of doing lines like this, maybe I want to connect them and make a shape and just kind of show the overall shape of the confidence interval. So I'm going to plot the same exact way. I'm not changing this plot, but I am going to add this polygon. So let me show you the result, and then I'll explain the code. So it looks like this. So essentially what I'm doing is I'm saying the x values are going to be the magnitudes, but then you'll notice here, I'm going to use this function called rev. This just takes your whatever function you have and it flips it. So the reason why I'm flipping it is because I'm having R go from here and it's going along here, and then I'm reversing it. I'm reversing the direction, so then it's going to come back down this way. So if I didn't do that, there would be a whole big line that just cuts this polygon in half because it's going to try to go from 4 to 5.5, and it's going to start over back at 4. So it's going to draw this terrible looking line that cuts across the entire polygon. So when you're making polygons, it's a little bit annoying, but you have to include this reverse for the second half of the polygon. If you're making a square polygon like that, you have to reverse it. Same thing with the y arguments too, because you want to make sure that the x and the y match up. So if you reverse one, you have to reverse the other. If you don't reverse either, you're going to have that line for sure. Now, this looks terrible, right? Like we don't want this to be our polygon. You would never really, maybe you would, but you know, you could find better ways to make it look pretty. So in this next one, I'm just going to get rid of the border of the polygon, and I'm going to color it blue with a little bit of opacity to it. So we show this. Okay, it looks a little bit better. Now the next step I'm going to do is I'm going to keep the same exact plot code, except I'm going to add in this little argument type equals n. I didn't include this before, but this means plot nothing. So when you plot it, it'll just plot the empty axes, and then you can fill it in. So then I plot the polygon on top of the empty axes, and then afterwards I'm going to replot what I had before, the points before. So exactly the same, but now I'm going to make it red. I'm going to make it filled in circle, and I'm going to add lines to it. So if I show what this looks like, now it looks like this. So of course you can make this green, you can make it whatever. But this I think looks much nicer than this one does.
Hey, Alex.
Mm-hmm.
What would be the motivation for using a polygon versus the confidence intervals you used in the previous example?
I think it's preference. I prefer the polygons in most cases, just because I think it looks nicer. But if you prefer these, then by all means.
Okay, I was just curious because I don't think I've seen the polygon really before. Maybe I have once or twice and I just forgot, but I thought it was really weird, but interesting. Like,
Yeah,
I see how it could work.
yeah. I think I prefer it. Like in this case, it's just pretty much like this is monotonic. But if there was something where maybe it has like a U shape or it kind of goes up and down a bunch and it's like wavy, maybe the
Okay.
polygon would let you identify what parts are above, like where's the confidence interval above the 0 point. But I guess you could just look at the confidence intervals themselves. Yeah.
Got it. Thanks.
Yeah. So it's just a preference thing. I prefer this, but do whatever you guys want. Okay. This next one is a question I get all the time. And I think it's a little bit counterintuitive. So I'd like to kind of go over it in some detail. So I'm just going to generate some diff and diff data. It's just super basic stuff here. So I'm going to have time is going to go from 1 to 100 5 times. So that's just going to be like 5 units. And I'm observing them for 100 time units. The states are going to be A, B, C, D, E 100 times. So super simple. My Y variable is going to be a noise term. So 500 random draws from a normally distributed variable. And then I'm just going to create this treatment variable. So if the state equals A and time is greater than 15, that's treated. If it's B and greater than 40, that's also treated. If it's C and greater than 60, that's treated. Otherwise 0. So if I just plot this and notice how for colors, I'm just matching state based on the letters. So this is just going to give me 1, 2, 3, 4, 5. So I'm just coloring based on numbers because I don't really care about picking the colors. I just care that they are different. And then I'm going to create some vertical lines where treatment occurs. So if we look at this plot, it's super noisy. But you can see, okay, the black group clearly gets treated after 15, right? You can see it jumping up here. Same thing with the red group, same thing with the green group. And then the 2 blue groups, it's a little hard to see, I apologize, but there's 2 blues down here and they're both hanging back. So typically with diff and diff, you'd like to see a line on top of these, right? So if I said, okay, let me just change the type to line, and that's all I'm going to change. Well, it only colors in one color, and it has these crazy lines that dart across the plot. And this is kind of what I was talking about before with the polygons, where if you don't reverse it, it'll go crazy across the screen, right? So what R is trying to do is it plots the first 100. So if in actuality, it plots the black ones first, and it goes up here, then it plots the whole way. And then once it gets here, it starts over again. So it goes back to 0 and then plots all over again. So it's making every time it goes to 100, it starts over at 0 and it makes this crazy line that goes across the screen. So that's not what we want. Also, it only plots one color because it doesn't understand what part of the line should then be what color. So it just picks the first one. So it's not that intuitive how this would work. So rather, instead of plotting it like this, you can plot this type equals n. So I'm just plotting the empty axes. I'm going to generate my vertical lines. And then I'm going to make a for loop where I plot the time series for each individual group. So for unique states, this is going to be equal to 1 the first round through the loop. And I'm just going to plot time where state equals 1, and then the y value where state equals 1. And the colors, I'm just going to do the same thing. So when we show this plot, now we can really see this is what like you would expect a diff and diff to look like if you had like weekly data or monthly data or something like that. So this to me is a little bit cleaner than this plot, it shows like clear jumps in the data. And I think it looks better. So when you're plotting multiple time series, if you have a panel data set, you got to write a for loop to plot all of your data. Are there any questions through this part? I think I've covered a pretty good amount of just basic plotting. You can always come back to this. I'm sure you'll have some application that will need some part of this at some point. But if there's no questions, then I'll just move on to the map section. Okay, so maps. So R was when it first was kind of on the scene, one of the biggest draws to it was its graphing capabilities. You can make really nice pictures, and I think people still claim that it's really great at that. I think all statistical software at this point is probably pretty good at that. Like I know Python excels at it, but R was kind of one of the inspirations for it was to have really nice graphics. So maps naturally lend itself to graphical analysis. So I picked some data sets just randomly. I was on New York City's data portal, and I just pulled 4 of them. So I have a shapefile of the 5 boroughs in New York City. I have a shapefile of every single payphone in New York City. This also includes ones that are out of commission at this point. I have all the subway stops, and I have this one data set, which is pretty cool. It's looking at the flooded areas of New York City from Hurricane Sandy from 2013 or so. So we're gonna kind of mess with these data sets and make some maps and do some analyses based on this. So this first one, go ahead.
Is GeoJSON the standard file format for R for maps?
Okay,
like shape is for ArcGIS?
Okay, that's a really good question. So shape files, so .shp are like, were the industry standard for a very long time. I think I would even argue that they still probably are in most circles. But if you ever worked with them before, you know that you get a file, and then there's the shape file, there's the DBX file, there's like a million different files that come with it. There's like 6 different files that you need in this folder to make it work. So what the GeoJSON file is it's all of that combined into one. So I like it a lot better because I can just read one file, save one file instead of having to save like a whole folder's worth. But this SF package, this read SF, can handle shapefiles, GeoJSON, and any other sort of, or most other spatial data files that you can imagine. Like for example, KML is another big one used by Google Maps. So if you're ever downloading Google Maps data, it's probably going to come in a KML file. You can use this same function, read SF, underneath the hood. It will look at the file, figure out which file it really is, and then it'll use the appropriate software to read it. It's this package is really, really powerful. So hopefully that answers your question. That is a preference, but I think it's there's a little bit more to it than just an opinion. I think it's much better than shapefiles. But anyway, so this first thing I wanted to highlight, just plotting a histogram. So what I've done is I've taken the installation date of all the payphones. I've used this function MDY for the date, which stands for month, day, year. If the date is in that format, which if you read it in this data and you print it, it will be in that format. It'll convert it to an actual usable date format. So you can do like date 1 minus date 2, and it'll tell you a difference of 8 days or whatever. Then what I'm going to do is I'm going to use this function called floor date. This is just going to collapse each date to its year. So the first day of the year. You can do this for month, week, day if you have like some time information. You can also use the year function, which will give you like 2006. But if you were to use the month function or the week function, it'll give you the week or month within that year. Whereas if you use floor date, it'll give you like 2006 June. So it gives you a little bit more information when you use floor date. But then I'm going to tabulate it, plot it. I'm going to make it look like a histogram. So it looks like this. So apparently in 1970 something, maybe 73, maybe this is 73, there was a pretty big spike in the number of payphones that were installed. And then again in the early 2000s. And then again, they're not payphones, but there are things called Link NYCs. They're like public hotspots. They're built over here, but I guess they're not in the data file. Okay, so this is just like regular.
All right, I have another question.
Okay, go ahead.
In your command xlab and ylab, were those from your plotting packages that you installed earlier?
So this plot function is just a default R function.
Uh-huh.
So if you go all the way up here, xlab and ylab are just how you label the labels, the axes.
So they're not in a particular package. They're part of the base R
Right.
program. Okay. Thanks.
Yeah, no problem. Yeah, so I just plotted these labels, and then I could have even put a main, main title up here if I wanted to. But anyway, so this is, if you remember, this is the only one I didn't read in as a shapefile. I just wanted to highlight that this one is actually a CSV. You can even see it's rows.csv in the link. So this is just text data, but I read in the other three as GeoJSON files. So New York City's like data portal is nice because you can select which format you want, but I wanted to convert the payphone into a shapefile or GeoJSON or some sort of spatial data frame in this tutorial. So that's why I did that. But for now, if I just printed payphone, it would just look like a spreadsheet. But if I print New York City, which is that shapefile or that GeoJSON file, it's going to look a little different. So the first thing to notice is it says how many features and fields. So 5 features mean 5 rows, and then fields is number of columns. So we have borough code, borough name, shape area, and then shape length. I don't think you'll ever really need these 2 things, but maybe they'll come up one day. And then it always includes geometry. So this is a multi-polygon, particularly because Queens, I think, has a little bit of like a island below it. So that's why it can't just be a solid polygon. There's the little islands and stuff like that off the shore. Now, some other things about it is it has this B box. So when you're plotting it, it knows what the boundaries should be for your axes. And it has this thing called a CRS. So a CRS you should think of as like how it's scaled. So if you look here, you can see, okay, this is definitely longitude and latitude. But a lot of times, if you want to do any sort of calculation or merging or distances, you're going to have to convert it to something called a state plane, which pretty much takes the curvature of the Earth into account and makes it flat. So you can do distances. Usually this is pretty easy if you're dealing with a city. Cities aren't that big. But if you're doing like distance from New York to LA, it'll make a huge difference if you're talking about latitude, longitude versus a flat Earth, for lack of a better term. So in order to do this, well, first I'm just going to plot the latitude, longitude stuff. So if I just plot New York City, I'm going to make border equals NA. So this is a slightly different thing. Before, if I wanted no border, I would do BTY equals quote N. I think maybe there's a legend thing. Maybe I'll show you later. But if you wanted to get rid of the border, you would use BTY. But if you want to get rid of the border of the shapes themselves, you use border equals NA. And then I'm going to color it based on whatever number it is. So 5, 2, 3, 4, 1. And I'm going to use an opacity of 0.2. And now for the legend, I'll put that in the top left. My legend is going to be just the name of the borough. The color is going to be the borough code. So that's how I'm matching up these colors. PCH is 15. That's just going to be a solid square. And then BTY equals N. That's going to have no border around the legend. So it's going to look like it's just floating there. So that's the shapes of New York City plotted on the map. Got a little legend here. And finally, I'm plotting the longitude and latitude of just this non-spatial data set, right? This is just regular CSV, read it in, plotted it. So that's why I used points here. And then I just colored based on if the payphone was active. It just randomly picked something. So if yes, it's going to be green. Otherwise, it's going to be tomato. So these tomato ones are dead. The green ones are active. So is there any questions? So this is just plotting a spatial data set and then adding on top of it another data set, but it's not a spatial data set technically. It's just text data. Okay, but of course you're going to want to do some sort of calculation with it. You're going to want to make it into a spatial data set. So how do you do this? Well, it's actually really easy. So you're going to use this function st as sf. And I'm going to say, take my payphone data. Here are the coordinates, longitude and latitude. And then that's all it's going to take. And once you do this, now it's going to be a spatial data set. But because it does you've just created the spatial data set out of thin air, it doesn't know what the CRS is. So before, the CRS for New York City was WGS 84. So what I'm going to do is I'm going to set the CRS as New York City CRS, because I know that they plot on top of each other really well. So now these two data sets kind of live in the same plane, in the same space. So now if I wanted to redo this plot, I would plot New York City's geometry. And then instead of using points or lines, or something like this, I would use plot, but now I'm going to include this add equals true. So you cannot normally do this with regular data, but with spatial data sets, you can. Add equals true, and it's going to give me kind of the same thing. I got lazy, I didn't color it as nice, but it's going to look the same. Okay, so now we have all these payphones plotted, but usually we're not just looking to make a map. Sometimes we are, but usually we want to do something with this map. For example, let's say this is Staten Island. I know that I want to want to assign each payphone a borough. I want to know which borough each one of these things is. So in your mind, you should be thinking about, oh, we learned about how to like merge in another data set, use the match function, right? You match years to years and states to states, and it merges right in. But if you want to merge based on space, you have to use some GIS tools. So if you want to find the nearest thing, well, let me start with join first. So st join will just take all of New York City stuff and all of the payphone stuff and just slam them together. So every single column in New York City will now be matched up to payphone and appended. So I don't show it here, but all it's going to do is just match it all up. So then you should be able to know which borough each of these things is in. So it's saying that, okay, this payphone right here is in Staten Island. I'm going to take whatever data is from Staten Island and put it next to it. Now, let's suppose maybe you don't actually have like a polygon and a point inside of it, like a borough and a crime or a house or something like this, but rather you have just a bunch of points all over the place. You have like police car locations, and you have crimes or something like this, like points on a map. You want to know how far each crime is to its nearest cop car or something like this, right? I'm just making these up. Well, the first thing you'd want to do is you'd want to find the nearest feature. So this is saying find for each payphone, find the nearest subway entrance. For some reason, you want to know for each subway entrance how far it would be to, you'd have to walk to call a friend or something if you're in trouble. I don't know. And then you can just pretend like this is the match function. So now you've made the nearest feature, and then you can just add the nearest subway is going to be subway name, and it's going to order it by the nearest one. Now, if you want to find the distance to the nearest thing, you can use st distance. So distance from each payphone to its respective subway. Now there's two things to note. First, I've included this m because I want to match up each subway to its, or each payphone to its closest subway. And I've done this by element equals true. So if you don't do by element equals true, it's going to make a matrix of distances. So for each payphone, it's going to find the distance to each subway. So instead of having like a vector of just however many payphones, it's going to be a vector of how many payphones, but the number of columns is going to be the number of subway stations. So it's going to be really massive. So it takes a lot of computation. So what I always try to do is find the nearest one and then take the distance. Are there any questions so far? I'm going to try to kind of fly through this. I don't have too much time, and I'd rather just kind of get in as much as possible and then have you guys look back. Okay. So now let's.
Sorry, it took me a minute to get my mute. The ST nearest and the ST distance, which packages are those in?
So anything that starts with ST is going to be part of the SF package.
Okay.
So all the spatial stuff is going to be from simple features.
Great, thanks.
No problem. Okay, so now let's start plotting some geometries. So I'm going to plot New York City, no border, color equals gray, and then I'm going to plot the flooding that happened in New York City from Sandy. So again, no border and add equals true. If I didn't use add equals true, it would make two separate plots. If you want to plot them on top of each other, you have to use add. All right, kind of cool. You see that obviously the flooding happened on the shorelines, right? And not in the middle of the city. That would make a lot of sense. But now if I wanted to really kind of work with these data sets and see what percent of New York City flooded or get distances, like even these distances and the nearest stuff, it was actually throwing warnings at me because it was working with lat long stuff. I didn't do it here because it takes a little bit of time to run all this code. But if you're going to do distances and stuff, you better convert it to state plane stuff. So this is a little bit tricky, figuring out how to convert to state plane CRS codes. It's not really like, you have to really Google it. Like, what's the state plane for New York City? What's the state plane for like Nebraska or something like this? You might have to Google it and find this little code. So for example, here's a website that lets you search for them. So here's a bunch, just the first top ones. If I want to type in New York, it gives me a bunch of different ones, but here's the one that's going to be closest, New York, Long Island. I've worked with New York City data before, so I just know that this is the one. But like New York West is probably going to be like Syracuse and Rochester and stuff like this. New York Central is probably going to be like Albany, or maybe even New York East will be Albany. I'm not totally sure. But there's all sorts of stuff here. So the one I picked was just 2263. So I'm going to take New York City, transform it to New York City 1. And I'm going to transform it based on this new CRS code, which is going to turn into a state plane. So if you're following along with me and you type in NYC1, hit enter, you're going to, those lat longs are now going to be very, very long numbers. It's converting to feet now. All right. So now let's say we want to do a diff and diff. We have housing prices, or we have subways, stops, or whatever, and we want to know the treated group is going to be subway stations or homes or whatever that got flooded. And then our control group is going to be areas that are just outside. So what we can do is we can build buffer zones. So this ST buffer will allow you to create a buffer that's going to be however long. I put 1609, thinking that this was in meters actually, but I'm just realizing this very second that it's actually feet. So this is a little bit short of, I think it's a little bit short of a mile. But anyway, you can create these buffers. And what I'm going to do is, so you have this red area, the buffer is going to go all the way around. But that's a little not right. I mean, there's not really a big problem there because for New York, it's pretty much water. That's the overlap. So it's not a huge deal. But if we were dealing with different states, then you might have spillover of the buffer. So what I do here is I use the intersection of buffer and New York City to kind of cut off any of the buffer that's running over into the water. So if it's in the water, I'm deleting that part of the buffer. If you want, you can run these codes and you can print each of these new objects each time and see how they change. But for brevity, I'm not going to do it. I'm just going to explain that this one's going to create a buffer that's like a bubble around the entire like peninsula right here. Whereas once I do the intersection, it's going to chop off everything that's in the water. Now this next one, I'm going to use ST union. So because each of these little zones, it's its own shape, these buffer zones are going to have a lot of overlap. So I'm just removing the overlap. It's mostly an aesthetic thing, but it will simplify some calculation later on. So now if we plot New York City, I'm going to plot my buffer zone that I've removed from the ocean and remove any overlap. And then I'm going to plot my sandy geometry on top. So now it'll look like this. So now you have your flooded areas, you have your buffer zone, nothing spilling out into the water, so it looks silly, and so on. Now you might notice that this red area is actually a little bit purple. The buffer zone, it's a little hard to see. The buffer zone actually will include the thing it's making the buffer of. So it's really just expanding out, but keeping the middle part. So if we are to figure out which of these subway locations are within each zone, if we do it, if we ask which one of these intersects with the buffer zone, it's going to capture both the buffer zone and the flooding zone. And then the flooding zone will only capture the flooding zone, obviously. So if I make a table of these things, I'll find that there are 100 that intersect with both, right? It's in M sandy and it's in M buff, which means that it's intersecting with both, which means that it's in the flood zone. But there's 560 that are only inside of buffer, but not inside sandy. So these would be like your control group, and these would be your like treated group. Like these ones got flooded, and these ones were just outside within a mile or 1,600 feet or something like that. Okay, so now let's plot it. This is a terrible plot because I've colored them the same as the space that I'm using here. So like black means nothing, but red you'll see here, I really should have picked different colors. It's inside the flooding zone. This red one is right on the shore here. These just cover up everything, so it's looks terrible. So I apologize for the bad coloring, but then the blue is in the buffer zones. Okay, so this is if you want to do like a diff and diff, right? You have a control group, you have a treaty group. Now, maybe you wanted to do a regression discontinuity. You want to take it to the next level. You want to know what's the distance from where sandy flooded, like what's the end line. So we can do a couple of things. So the first one we're going to do is we're going to generate just the outer boundary. So we have our flood shape, And we're gonna, for each of these shapes, we're just gonna make outline. And we're gonna find the distance from each point to the outline. So I'm making the boundary here. I'm finding the nearest feature for each of the subways. And then I'm finding the distance. So I've done this all before, but I'm just calculating the same exact thing. So now if I plot a table of the distances, but what I'm gonna do is I'm gonna make a modification and I'm gonna say, if it's in Sandy, make this a negative, because it's actually on the other side of the border, right? So if I show this plot, we'll see, okay, here's 0, where I'm rounding. Here are the untreated groups, and here's the treated group. So you can see that there's obviously more outside of the treated group and then some inside. But this would be a way to do like a regression discontinuity. Maybe if you had homes, maybe make a little bit more sense than subway stops. It was just a nice little data set that I could manage and stuff. And then you'll also notice how terrible these, it just puts whatever you put in there. So you're going to want to label all these axes and stuff like this. I just got lazy and didn't do it. Okay, now let's think really hard about this. I've made a border, right? I've made like a circle around each of these flood zones. If one of the subway stations, like that one on Staten Island, was really close to the edge there, it might actually be calculating the nearest feature as the shoreline, which would be a very, very small distance. Whereas in actuality, it's very deep into the flood area. So I might need to be a little bit careful, and maybe I want to find the distance from the buffer zone, the start of the buffer zone, instead of the end of the flood zone. So there could be differences in how you're calculating it. So in order to do this, my idea was to find the distance from the subway to the nearest flood zone. But now I'll remove the overlap in the flood zone and the buffer zone, and I'll do the same sort of thing where I'm looking at the ring of that. So blah, blah, blah. If we make a bunch of GIS calculations here and make a bunch of different shapes, we can make the same exact plot. And we get a little bit different of a shape, but pretty similar. Now, if I wanted to kind of check these two things against each other, which one of these is quote unquote more correct, I can plot the original distance to the second distance, this one. And they're pretty spot on. They're pretty similar. There is a little bit of difference going on here though. So I might want to try to figure this out. So what I've done is I've taken this group right here, which says, according to the original distance calculation, is quite far from the flood zone, but according to the second one is actually very, very close. So I'm going to just plot the ones that are right in this little section. And if we plot in Manhattan, here's just the place in the flood zones. And then here's including, with the buffer, here's the buffer in the flood zones. And then I'm going to add in those points. And these red points are the ones that I was talking about. So those red points are the ones that are going to be right here, meaning that they're the ones that have the most difference in the first and second calculation. And if you look, they're really right on the edge here. So in actuality, these are quite far from the flood zone. So this second calculation is probably not to be trusted, right? This one's probably bad. So this is how you make cool little maps in R. A couple of other notes. You can use a bunch of different parameters that you pass to R to change how your plots look a little bit. For example, this par is going to have pretty much everything. So there's margins, and then there's a number of plots. So MF row. If you plot different margins, it'll get bigger or smaller. So this is just like the default, right? If I change my MF row to be 1, 2, it'll plot 2 next to each other. This sometimes is desirable, sometimes it is not. Sometimes you just want to have 2 pictures and put them next to each other in LaTeX, but sometimes you just want to do it in R, it's up to you. If you want to use your axes, you can turn them on. By default for GIS data, it's turned off. So the default is axes is off. And then you can change the margins. So the original margins are 5.1, 4.1, 4.1, and 2.1. That produces this. But if I set the margin to 0, meaning I'm cutting out the axes, like the axes are the edge of my picture, I'll get a little bit more zoomed in. It's just a little bit of some notes here. I think the margins in R are pretty large, and you can kind of trim out some space if you want to. But anyway, that's all I had. It's a lot of information, a lot of plotting, a lot of trial and error is going to go into a lot of this GIS stuff. I'm still learning it myself, but I've found it to be very, very helpful, especially when you can write programs for it instead of using something like QGIS, where it's more point and click. So replicating things is a little bit harder. But QGIS is still an excellent tool if you can code in Python. But do you guys have any questions or comments, concerns?
For ST nearest feature, can you go back and explain that syntax one more time for me?
Yes. Trying to find it. Okay, so the way let me find the first instance of it. Okay, so nearest feature. So I want to find for each payphone, find the closest subway. So it's really just 2 arguments. It's 2 shape or 2 GIS files. The first one being the one you want to find the closest thing for. So you should think of this as the match function, but spatial. So the match.
So both of those are points, right? You can't do that to a polygon, like a point to a polygon.
You can. So I do that again down here, where I find the nearest feature of the subway to my sandy boundary. So that's going to be the boundary of all the red stuff. So you can do either way. I should mention that there's way more information that I could ever go over here and here. So this is essentially a textbook. R is GIS for economists. You can learn so much in here. I only ever really go in here if I'm trying to figure out how to read and write data, because I always seem to forget how to convert text data into spatial data. But there's another cheat sheet here that has all these SF functions for you and has a little bit of an explanation and a little picture for you. So if you wanted to look for nearest points or nearest feature, XY creates an index of the closest feature between X and Y. So this thing I have bookmarked, and I go all the time, once a week for sure.
Show me again how you got the cheat sheets. Where does that come from?
Yeah, there are more notes on SF and spatial stuff in R here and here. You just Control F here and here. Sorry, that's really not intuitive. It'll be there.
Okay.
Do you think you make more maps, or do you aggregate data more in your work as an applied economist?
Aggregate data more. I aggregate data for every single thing. I always want to see like aggregate relationships instead of just massive, especially when you're working with big data and you just want to see the general relationship instead of like some massive scatter plot of like 40,000 points. It doesn't really mean anything. But if you have like aggregate relationships, it's a little bit easier to visualize at least what's going on. but I like making maps more, if that's anything.
Yeah, it seems like the better the graph, the better the publication possibilities too, right? It's like, yeah, the purpose of a plot has really gone up, in my opinion, in a lot of ways. You don't have to say as much anymore either.
Right. I think like the pictures that you see in RD papers are like really what convinced me that if you can show something graphically, you're done. You don't like, even with a synthetic control, if you can show a synthetic control that really pops, you're done. The paper is like, you know, you barely have to write it because the picture is so convincing. So yeah, if you can figure out a way to show that, like that plot that shows your effect or shows your identification, then that raises your publication by half a letter grade or whatever. All right, I'm gonna stop recording.